All right, here we go. First class, first semester, first time at Clemson. Welcome back. I always like to say that since this will be on YouTube. You know what I have to tell you all, right? Hit that like and subscribe. Smash the bell, right? And I kid you not, Lisa Hoffman has merch, but it's specialized to her. I bought her that for her birthday once. So if you ever think of merch ideas, let me know. But anyway, the full YouTube experience, that's not what we're here for. We're going to talk about, I call it a review of descriptive statistics. I assume you've heard about a mean before. So we're going to start there. Conceptualizations of variance, and then I added a linear model component, and of course I didn't change the title. So here's where we go. I hope the typos are fewer in number this time. And of course, click PowerPoint template. There we go. Our objectives today is for the descriptive part is to just remember, just refresh central tendency. How do we describe data? Variation spread, bivariate descriptive statistics. Really, the point of all this is to do a couple things. You probably know about correlation. How familiar are you with covariance? Because covariance is correlations like, like the black sheep of the family, like or whatever you want to call it, the redheaded stepchild. I don't know. I'm picking on like entities I don't need to. Evil correlation. I don't know. Harder correlation. I want to get into covariance a little bit. I also want to talk a little bit. I don't believe I have. Actually, I think I took this part out, so I didn't update this. Sorry for that. The data for these lecture, by the way, in Canvas, you will find, and soon to be on GitHub, you will find this set of slides for the PDF. And then in our data file and in our script, you don't have to, since we didn't put R first, I'm not showing you that. I'm just going to talk conceptual here, okay? But if you'd like to follow along, you're welcome to. These are the variables that we have in the data set. Not a whole lot here. We've got a person's, their sex, biological sex, male or female. You have, and I've just limited it just to male, female, just for the simplicity of this analysis that we're about to get into. We have height in inches, we have weight in pounds, so that is our data. The endpoint of this lecture will be to build a linear model that predicts the person's weight. That linear model, what a linear model is, the way I use that term is a statistical model for an outcome that uses a linear combination, which is that sum of beta weights times regression predictors of one or more predictor variables to produce an estimate of an observation's predicted value. Why this is showing up here is that I really wanted to, again, establish that models underlie all statistics, right? Almost everything we do is a model, even when people say, oh, it's non-parametric or, it's not, there's always some model there, even if it's not implied, even if it's not explicitly stated. For instance, in homework, number correct, you add things up. That's actually, it actually is a very simplistic factor analysis model, believe it or not. All right, so we'll move forward. There's our data. I have a terrible scatter plot here. By the way, I took these data. The UCLA has a statistics website, IRDS, something like that. Borrowed these data from them. I'm pretty sure these are simulated because when we get to the final result, you'll see lots of things. There's not a lot of noise, clear separation between male, female, and so forth. So here are the height and weight histograms right here. And the weight variable is certainly bimodal. All right. When you see that, do you get worried? Let me ask that question. What do you think? Does that worry you?
Yes.
Why does it worry you? It's not normally distributed. That's a great thought. And we get taught that a lot too, right? But does it need to be normally distributed?
Isn't that like the premise of statistics?
No. And that's what I want to teach you in this class. So, and that's the interesting thing. So I have been in stat classes where you will, and actually I took stat classes where you'd see that and you'd say, what do I need to do with that? Because I want to make it more normal. And so you would transform the data or whatever. But it turns out in the model we're going to build, we want to predict weight. And once we go and specify the regression line itself, what we're going to see is the assumption of normality does not apply to y, the outcome. It applies to what's left over. And so once you predict it, if what's left over is now not normal, that's where the problem lies. And it depends on, and actually there's like normality is the least of your concern. Honestly, it's one of the more robust distributions, and so based on that, if it's slightly non-normal, it doesn't change a lot of your results. Now, heteroscedasticity, not constant variance, that's a big problem. But so when you see this, that's why I wanted to bring this up here. I was going to talk about like challenging conceptions in statistics. Nothing needs to be normal. And in fact, if you were to transform weight and put it into a regression, you would actually end up changing the regression slopes, which means your results and interpretations and conclusions might change, right? Because now it's no longer really weight that you're doing, and it's really hard to untransform it. You've changed the effects of the predictors on weight when you do that. So I wanted to point that out. So thank you for volunteering. I don't mean to, I hope I wasn't like, no, you're wrong, but it was, that's a very common conception in statistics that, oh, it must be normal. Honestly, like modern versions of statistics say, it's all right. We have a distribution that'll fit it. It'll be if it's not normal. But in this case, what we're going to see is it doesn't even need to be. Okay, so we have those two variables there. And this is the marginal joint. This is language of multivariate, and actually language of more of on the theoretical side, but it shows up sometimes. If you summarize a variable by itself, we often call that a marginal summary, right? One variable by itself, right? And so common versions of why is the extra language there? Well, the extra language is because multivariate distributions actually have more than one variable, which are also marginal, but then they start becoming what we call joint distributions, like two things varying at once. When we have one variable and then we want to summarize it by itself, the common descriptive statistics are used to it: the mean, the central tendency, the median. If the data are skewed, you would probably want to pick a median. The mean is the most sensitive to outliers and to deviations of some random chance. Median is less sensitive, and then the mode of the distribution is even less sensitive than the median. And then if you want to talk about how wide the data are, how spread out they are, that would be a measure of variability. A standard deviation is one of that, or standard deviations, lesser known or lesser thought about components, variance. You can talk about the range, and there's all sorts of ranges, right? Interquartile range you may have heard of. And I'm not the guy to probably tell you all of them, but that's sufficient for us now. By the way, as I lecture, since it's the first time I've actually lectured to you, please stop me with questions. Please interrupt me. Please, and let me also tell you this. I respect every question. No question is too basic. No question is too hard. If you have a question, I will treat it with respect, and I encourage you to say it. And again, if you put it in the chat, I won't even tell you. If you're worried about that, if you put it in chat, even if you log into Zoom here, I won't say who put the question out. So if you're worried about that as well, I understand that being a grad student, if you were like me, you didn't want to look, like you didn't know something in front of your peers. So I want to minimize that as much as possible. Okay, so that's one variable. But if we have two variables or more, like height and weight together, then what we want to do is summarize the joint distribution, right? Or sometimes called a bivariate distribution when you have two variables. And joint really just means more than one variable simultaneously, right? So that's it. They're very hard to plot, especially after you get more than two. Like you can think of, like if you think of a normal distribution bell curve, you could probably draw a second dimension and have like an actual Liberty Bell looking thing. But after two, it gets really hard to plot them, right? Now, some multivariate techniques are great for plotting, like principal components analysis people try to do to sort of aggregate data down into a space you can see it. Or, of course, the network statistics network work does a lot of that as well. So this is where when you have more than two variables, creative descriptions and plots work. Now, when we want to describe the behavior of two variables, we often use correlation or covariance, right? And turns out correlation is a rescaled version of covariance that we're going to talk about in just a bit as well. How we doing? How's the pace? Everything cool? Okay. So I apologize for the black and white here. I tried to find the Clemson slide style, and then none of the tables came through with the Clemson colors, and I I literally am looking at the clock like I'm never going to get this done if I color it the right way. So we have old black and white font here, but at least it hopefully is visible. These are the descriptive statistics. We have the average height of a person is 67.9 inches, average weight's 183.4 pounds. And honestly, if you look at 183.4, that falls where nobody is. So that's another interesting feature of a bimodal distribution. Um, and there's exactly half of the data set are female, it appears. The standard deviation of height is, again, 7.44. And the variance is the standard deviation squared, right? So we often don't talk about variance. I'm gonna have more on that in the next slide. And then down below, I have a correlation or covariance matrix. The bottom part of this, if you're familiar with correlation matrices, those are correlations, right? So the correlation between height and weight is 0.798. So that's a pretty strong correlation. The correlation between height and female is negative 0.593. That is also strong. And then weight in female is also negative 0.955. So this is another indicator that this is going to be not true data, right? Finally, or actually, then normally you have a correlation matrix with ones down the diagonal, right? It turns out, as you might remember, correlation is sort of well. Let me back up here. The ones right there, it is the relationship of basically standardized variables, right? So that variance of a standard, like a z-score, would be 1. That's where that happens. But in our case, the diagonal, I've replaced the ones with the actual variances of each of the variables from right here. And in the upper triangle of this matrix, I put the covariance. And again, covariance, those numbers are really hard to interpret, right? What does a 334.832 mean? And we're going to talk about why that is in just a slide. Any questions so far? Okay. Oh boy, formula. I don't want to go deep into this. By the way, I'm not going to ask you to memorize any formula. I put this up here not for comedic effect, but more to point out a couple things here. Let's talk a little bit more about the concept of variance a little bit. It's a really core concept in multivariate statistics, and variance and covariance, that is, right? And actually, these got moved up, and they should be down here. You may have seen the standard deviation formula before, where you had an n minus 1 in the denominator. So basically, you take each observation for a variable, you subtract that variable's mean, you square it, and you sum them all together. And then you have to divide by n minus 1. You may have heard of that as the sample estimate or an unbiased estimate. But then there's the one with n, right? Turns out, interestingly enough, why we do this, biased or population, you may have heard that. Turns out the bottom one, if you do statistics that use maximum likelihood, this is the style of variance that you get out of it, right? So if you're doing, my gosh, it starts with the V. Victoria? Virginia, my goodness. I should know better. Virginia, you were mentioning linear mixed models and what they sometimes called variance components. So you get random variances. Depending on how you estimate them, if you use maximum likelihood, they're biased. But then there's another estimation method called residual maximum likelihood, or REML, R-E-M-L, and that tries to correct the bias in maximum likelihood. So this is where I'm trying to introduce, like, when you learn this and you learn population versus sample, really what we're talking about, honestly, that's the translation of maximum likelihood versus least squares. That is the difference between the two. And why population shows up here is population, we think n will be very large, and that -1 as n gets big matters less. The size of the discrepancy gets smaller and smaller and smaller and smaller, right? Like 1 over, if you have 10 people, it's 1 over 9 versus 1 over 10. That's not, I don't know what that is, but if you have 1,000 people, it's 1 over 999 versus 1 over 1,000. There's not much difference between the thing that multiplies it. How are we doing so far? Okay. And the owl, I can look into the owl and see you online, right? So by the way, those of you online, next week I'm going to change the setup. I have to sit in this weird angle because the cord is short. But next week I'm going to reposition myself in where I can have everybody in front of me and look right at you. So I'm looking at the screen, but I'm not even looking at the people in place here. So I know that's another part that's difficult. But let's talk about what variance means, right? If you think about this term here, this is the variance describes the spread of a variable in squared units. Now, if you remember, true story, I'm almost a high school dropout. I don't know if you know this about me. I would have never gotten into Clemson as an undergrad. I failed math, of all things. So seriously, I did. It was a stat class in community college that turned me around, and but I remember in chemistry in high school. If you ever took chemistry in high school, remember there was this unit in chemistry called stoichiometry, where you had to like cancel units and so forth. Turns out that applies to variance and standard deviation. So if you look at the equation here, all right, let's take a look at this. The sum of something divided by n is a mean, right? If we just had the sum of y here divided by n, it'd be its mean. But this sum is not y, it's how far off each y is from its mean, right? So it's the average deviation squared, right? So if y happens to be pounds, weight in pounds, when we square that, just like in chemistry, it's now pounds squared. So variance is in pounds squared, right? So height is so the variance of height is 55.358 inches squared. The variance of weight is 3,179 pounds squared. And then the variance of the female variable, again, I coded it 1 as a female, so that's why I'm calling that instead of sex. It's not applicable in the same way because it is a binary variable. And so it doesn't really function the same way. So variance to me is how far off the average square distance is. And if we took the square root and got back to the standard deviation, then standard deviation represents the average distance from one observation to its mean. Right? So on average, each observation is about 7.5 inches away from the mean of height. That's how we interpret the standard deviation. Sarah, I know you mentioned interpretation. I'm trying to interpret these things that are somewhat like we sort of take for granted a little bit, but it sort of describes how they move away from it. The standard deviation of weight, on average, a person is about 56 pounds from the mean in weight. And again, why that is, if you remember that distribution, the mean happened to be near nobody, right? So that's a very far distance on average from any one case. So it turns out like variances and standard deviations are averages, but averages of deviations, which is an odd way of thinking about it. How are we doing so far? Okay. All right. So it turns out this idea of variance or standard deviation is a more general statistical concept because we just used it to describe our data, but you know, and in fact, in an introductory statistics class, shortly after we teach the standard deviation, we often talk about the standard error of the mean because we have to form it using the standard deviation of the variable divided by the square root of n. What that really indicates is that, so standard deviation or variance of your data talks about how far each observation is from its mean. But in a statistical sense, for a parameter, if you talk about the mean itself, its standard error talks about how much variation the mean might have based on the sample that you have, right? So each parameter will have uncertainty as well. So in your model, like, so what we're talking about when I say uncertainty, if these were 0, everything would be a constant. We would be certain what the value is. But these are measures of how uncertain we are if we were to think about a variable. And the mean and the parameters of a model or the mean itself, any type of statistic that you can come up with, also has uncertainty to it. And that is the hard part about statistics. There's 2 bits of critical information that we have to learn. One is, what is the parameter? Like, what is the mean or what is the predicted value? But to really understand statistics is not just about understanding what that prediction is. It's about understanding how uncertain or how certain that prediction is, right? So if you see a very large standard error of the mean, it tells you that the mean may not be doing a very good job of describing where central tendency happens to be because there's so much wiggle room to it, right? So when we say standard error is just another name for standard deviation, right? Its standard error of the mean is the standard deviation of the mean, right? And to establish why that is, we have to think of things like maybe you've when you thought of the standard deviation of the mean, that's where we talked about sampling distributions. Do you remember those? Where we had to talk about doing an experiment with replacement and over and over again and calculating means from each of the same sample sizes and how much those means vary. That literally is describing that standard error of the mean. So generally speaking, variance is another term for error, or how far off you are potentially in your statistic, right? You can think about the standard error of the mean as telling you how far off the mean is for describing the data, right? And standardized units. So how we doing so far? Oh, I have a hand. Yes, Colin. So let me just like talking about. Please do. We're saying standard deviation. We're saying, all right, we have this sample, we have all of these numbers in this sample, and it's just how much essentially they like what happens they vary from each other. And then the mean or the standard error mean would be essentially now let's take the population that the sample comes from and how many different means might we possibly have been able to pull from that sample. That's it. That's it exactly. That's it. And how much wiggle would those means have? Exactly. Right? Perfect. Great job. Other thoughts or questions? Yes. So I will warn you, I'm sorry, I feel a little like I have to prove myself tonight. So if I'm going too far, let me know. Yes.
I have one thing, the one sentence. Just make sure I'm thinking of this right. Variance equals error. Is it a good thing that you are accounting for more error, or is it a bad thing that you might have more?
I think it depends. I think it's let's go philosophical. Okay. It just is. We have to be. It's just the way of the world. I know it sounds bad. I think as a statistician, error is confidence, right? A lack of confidence, right? And so, generally speaking, we want to be accurate about how much error there is, because otherwise we don't know. We're going to either be underconfident or overconfident in our result. So I wouldn't necessarily characterize it as. I mean, if you're defending your PhD and you want to publish, you want less error because you want to
be confident in the model.
Exactly. That's it. Exactly. Good question. Okay. Should we keep going? Virginia. Got it? I got it. Okay.
If it's just the state.
That's it. That's it. Good. Okay. Let's talk about correlation, though. Oh, God, that's a terrible formula. By the way, if you asked me to put that formula down, I couldn't tell you. I've been doing this for years. I couldn't tell you. Okay. But it again, look at the numerator of this thing. You've got n minus 1 here. That is interesting because it's like an average, but the minus 1 doesn't make it. So when you see sum of something over n, think average. It's the average what? Okay, so it's a variable minus its mean times another variable minus its mean, right? So it's the average of the product of how far off those variables are. That's crazy. I don't know how to interpret that, right? It is a very difficult statistic to understand. The numerator of this, at least. Whoops, excuse me. But then we divide that whole thing by a standard deviation of each variable multiplied by each other. And I'm going to talk about that just a little bit, but actually I'm going to talk about it now. Correlation is unitless. So before I mentioned variance. If I were to talk about the height of the variance of height, it's 55.358 inches squared. The numerator of this thing turns out it's actually, we've got units of y1, we've got units of y2. But then we're dividing by units of y1, and we're dividing by units of y2, right? And because we've multiplied them together here, we multiply the units down here, we've effectively removed the units from the numerator and the denominator of the equation. And this is going back to that high school class that I failed, not the teacher's fault, where you basically removed units from the equation altogether. So correlation is nice because it's unitless. You can use it for pounds, you can use it for inches, you can use it for kilograms. It doesn't make a difference. It still describes the relationship of variables, and it's really understandable, right? This correlation is what we would sometimes call the Pearson or a Pearson product moment. God, those terms. Correlation, it's used for continuous variables. If you don't have continuous variables, you may have heard of other versions of this. So if you have binary or categorical variables, sometimes we call it the correlation of a binary or categorical variable with a continuous variable sometimes is called point biserial, point being the binary variable. And then a Pearson correlation of binary categorical variables with other binary categorical variables has bounds between -1 and 1. Actually, this is not entirely the case. Pearson correlation of binary variables, and here is a mistake on my slides. Only under certain circumstances does it range from -1 to 1. There's actually other correlation statistics out there. I don't know if you've heard of tetrachoric correlation or polychoric correlation. Are those terms you've ever heard before? I'll bring those to this class. That's a multivariate technique right there. The problem with binary and categorical variables is that the maximum range for the variance is mathematically restricted, right? In the binary variable, I think you may have seen it here with the variance. This can't be 0.5, by the way. The variance needs to be, well, I guess, yeah, anyway. The variance is the mean times 1 minus the mean. And so in those variables, because the variance gets restricted, there's only so much that can happen, it changes the range of the Pearson correlation. So it may not range from -1 to 1. It may range, and so that's a little bit dissatisfying, and it's really hard. It's no longer completely standardized then, right? It's not the same metric. But I will show you the tetrachoric and the Pearson, because that does, or the point by serial correlation, because that does come up. Yes.
Spearman come into play.
Spearman is a rank correlation. So it is what, instead of using the actual quantitative numbers, you first rank your variables.
Okay.
And it sort of correlates the rank order of the variables itself.
So the higher together, the higher together.
Exactly. And it's used in cases where your variables maybe not continuous, right? Or maybe not entirely continuous. Or better yet, if you want to talk about, you talked about 5K earlier today. You want to correlate the 5K in Seneca, the results with maybe the same people ran 2 or something like that. That might, but all you have is the rank order of people. Yep, that would do it. How we doing, everybody? Questions? Okay. All right, so a little bit more on the correlation coefficient. Ignore, if the equations bother you, just try to block them out. You don't have, you never have to remember any of these, okay? Just, I'm using them to sort of describe it. And in a language sense, I want you to be able to sort of read them a little bit better. So the more I do it, I feel like I'm trying to immerse you in a context where equations matter. But please, if they're intimidating, I understand. Believe me, when I'm I've been editor of journals. I've been I'm an associate editor for like 2 journals. And when I get to the equations, my eyes want to skip over them as well too, right? So I get it. I totally do. I do read them because I have to do a job to edit, but it's harder. Turns out, you know how in standard deviation, we made a big deal of bias versus unbiased population? What if I told you the correlation's biased? How'd you feel about that? So only does it matter. We only talk about that in basic statistics when it comes to standard deviation or variance. We have n versus n minus 1. It turns out correlation's biased as well too. And if you wanted to correct the correlation bias, there is a formula for it. I had to look this up. There is a formula for it, right? And again, as the n gets large, the amount of bias starts to shrink, right? The n goes large, the bias goes away. The bias is largest when the core, and also as r squared gets large. The bias is largest when the r is actually 0. So the Pearson correlation actually underestimates the true correlation. This thing that you're multiplying by inflates it a little bit more. Isn't that crazy? Anyway, why would we're all okay? We got to worry about bias, but only on some statistics. Isn't that weird? But why I bring this up is if it is biased, why does it use everyone? By the way, bias in statistics refers to your point estimate will have a systematic deviation from its true value. That's what bias is defined as. I should have defined that earlier, right? So meaning if the true value of a standard deviation should be 5, your estimate of it may be 4.75, right? That's what we would call a bias in statistics. If you have biased estimates, why does everybody use it? And the answer happens to be, it turns out that a lot of statistics are biased. What we want is, that's sort of the idea of some of what sometimes we call it frequentist statistics, is the sample size gets larger and larger, the bias source goes away. That is a lot of when you hear And you hear people say, oh, that's a large sample technique, that's a large sample method. That's sort of implying it needs to be large sample because the error or the bias is large in smaller sets of it. Everybody are doing okay? Again, this is a weird take on it, right? I told you to be the sort of the intro, but now I'm like, okay, let me sprinkle in some other stat things. So the covariance, turns out, is the numerator of the correlation, that thing on the top. And going back to the idea I mentioned on the correlation slide that we could cancel the units, we don't use covariance much because the units are still attached. So the covariance of height and weight was 334.832. But what 334.832 what? They're inch pounds. Ever heard of an inch pound before? I don't know what that is. I remember, okay, so another true story. I may have almost dropped out of high school, but I did know enough to know how many classes I could fail and still get one fewer class period in my senior year. And I also knew that even though I failed chemistry, that at the time in the 90s, auto shop counted as a class. And I say that because in auto shop, I learned of a unit of centripetal force, or I don't remember which one it is, torque. Have you ever heard of that before? Like when you hear about, it's usually truck commercials, you talk about the amount of torque you've got, right? Because it's like something with the engine. They always talk about foot-pounds of torque, right? It's the same idea. Like it doesn't make any sense, but evidently we're going to talk about it. Evidently, it's okay to sell trucks, but not so much in statistics. But yeah, covariance is a when we get into the talking about distributions, covariance is actually what's in the normal distribution, right? In the distribution, there's a function that describes the shape of a curve, and its parameter is not correlation; it's actually covariance. And the same thing happens in the normal distribution when it comes to variance and standard deviation. They show up in the variance is in the normal distribution up in the exponent as well too. So we use covariance because it's sort of the central core of these distributions, but nobody talks in covariances, so we describe it as we would go and describe it as a correlation. So it turns out covariance, and because right here it's the numerator of the correlation, you can switch between the two, right? If you have a bunch of covariances, right, all you have to do is divide each covariance by the product of each variable standard deviation, and you get its correlation. Or if you want to go from correlation to covariance, you have to know the standard deviations, but multiply it by that product, and you get the covariance back. Yes, Virginia.
When you talk about it as it's similar to the distribution, if you were to take your belt example and put it on an XY plane,
yeah,
the covariance is the distribution being measured in that like 3D.
No, so what I was meaning that if you have the Bell example, yes, the covariance describes the sort of if you were to fly over the top of the distribution and look at its shape, almost like a contour map, like you were hiking.
Yeah.
It will describe, like a correlation does, how shaped it is, how elliptical versus how not. So no correlation, covariance is a circle, and then high covariance is an ellipse, or and like actually with the covariance that would be equal to a correlation of 1. Now that would be where the numerator, it consists of, basically it sums to the product of the standard deviations, is straight line. But now here's a multivariate talk. I like this question. If you wanted to talk about what you were saying, which is sort of how that shape fits in each dimension, we can take that covariance matrix. So you put the variance at the diagonal and the covariance the off diagonal. We can do a bit of math to it, and we can actually come up with how far, like what the sizes and how far the ranges are. It's sort of in the classical version of this class, people end up spending a lot of time on that. I'm not as much because I think we just display data more. But that's very good intuition, though. Exactly. The covariance matrix, interestingly, or correlation matrix, both of these are huge problems in data. Now, I say that now in the year 2026, in a lot of places, people forget that people are still collecting data by hand. So if those of you are collecting your own data by hand, this does not apply to you. But in a lot of places, big data shows up everywhere. So you have a lot of you're collecting data off of eye tracking, or like fMRI neuroimaging, or all these ways. I I actually consult for a baseball team, and they have pitch trackers that talk about how much distance or whatever pitches moved or so forth. So there's a lot of data. We often want to the principal components analysis and techniques like that try to take all of that information about how variables relate and boil it down into something more understandable. Because as you get more and more covariances, we're talking about one at a time, but synthesizing or describing how data work when you have 15 or 30 or 100 is really difficult. So that is one of the techniques. So my purpose of putting this in these slides is covariance never shows up in introductory statistics or regression class. Rarely, maybe in regression, maybe because of how you calculate partial and semi-partial. Anyway, so, yeah, never mind. So I'm talking about it here because it does show up frequently in multivariate statistics. Okay? But if you don't know how to interpret correlation, I also don't know how, because an inch pound does not make any sense. Okay? Okay. Unless you're selling trucks, I guess. All right. This is how you switch between the two. Literally just a little bit of math, right? So this also helps me say correlation is covariance divided by the product of those two standard deviations. That's how correlation is. All right. That was the first section. How are we doing? Too deep? Too different? Okay. I'm learning how I need to teach here. So please, sorry, you're all members of a horrible experiment. And I realize we actually have those of you who aren't in here, I don't know if you can see behind my shoulder, this glass is a two-way mirror, I just noticed.
Yeah.
So I might be being observed by the dean, or provost might be in there watching me try to fail in my first class. Oh, yeah.
Parents can watch the kids.
Yeah. I was just looking. Oh, yeah. Oh, it goes. Okay. I was thinking. Oh, that could be. Oh, let's watch. Let's see if we should really let him be hired. I don't know which way. I can't tell. But as I saw in here, I'm like, oh, look at that. Anyway, so okay. Shall we go into a linear model now, a regression or ANOVA? All right. This is where we talk about a conditional distribution. Right. So before we mentioned the word joint distribution, which is two variables at once, like the bell curve, but in multiple dimensions. We talked about marginal, which is if you took that bell curve in multiple dimensions and smash one of those dimensions down, you just get the regular drawing of the bell curve. That's marginal. And now what we're going to talk about is saying in those two dimensions, if you take a value of x or one value of it, and then you just condition on it, and you look at all the values of the other variable, that's what's called a conditional distribution. It turns out, if you've heard these terms, regression, analysis of variance, analysis of covariance, or analysis of covariance with interactions, which doesn't have a name, those are all really specifying models that are implying conditional distributions, meaning we're looking for the value of y conditioning on certain values of all the predictors, the value of an outcome conditioning on the predictors. So here is, you may have seen this before. If you have one y, one outcome, one variable you're predicting, and you have a bunch of predictors that are categorical or discrete in nature, right? Like our female variable in this example. Often we call that an analysis of variance. If you have continuous predictors, so like the height variable in this case, if you just use it, you might call that a regression analysis. And if you have both types, you might say, oh, I have analysis of covariance. I don't know why covariance shows up there, but not over here. That's kind of weird. Now in this class, because we're doing multivariate, we will get to where we have multiple outcomes in a model. If you still had the same categorical predictors, and all of those predictors were predicting more than one y, y1 and y2 or y3, right? We would call that, we put an M in front and call that multivariate analysis of variance. Honestly, multivariate analysis of variance sounded really good in the 60s. Functionally, it's not really all that glamorous. It doesn't give you results. It tells you if there's any trend overall on any of the variables, then you have to follow up with it and do univariate ANOVAs. So you're back in the same spot that you would have been without multivariate, and they're all the same results. Now, if you have continuous x's, that's called multivariate regression. And if you have both, I like this word, multivariate ANCOVA, MANCOVA. That just sounds kind of funny, right? Now, in each of these, the typical assumption is that the residual or error term is normally distributed, right? So that means if you were to do the math through this, as I mentioned when we talked about that bimodal variable, y itself, the outcome, is not normal. It's what's left over, e, error, that needs to be normal. And then if you have models for non-normal outcomes, like dichotomous or categorical count, we often call this the generalized linear model, which is kind of funny, right? The general linear model is like 1950s and stuff. And then as we're getting better at about different types of data, someone's like, well, it's not general. What are we going to call it? Well, generalized. It's all funny. Too much, right? I know it's 7:15 at night. Look, like, you know, my partner is Lisa Hoffman, so we talk statistics at night. So if you're not used to talking statistics at 7:15 at night, I feel for you. I understand. Oh gosh, I have red and blue on this. That must be KU. I worked at KU twice, right? So if we look at a model, so here, this is a general linear model. Why I can diagnose it as that is that there's this error term at the end. In the non-normal types, this thing gets a little more convoluted and error starts to be harder to find. We often have our outcome y for a person p is equal to this regression line where you have an intercept, beta 0, which represents the value of y when each of the predictors is equal to 0. You then have a regression slope multiplying x, which represents the increase or change in y, can be increase or decrease, when x changes by 1 unit of x. Again, what a unit of x is on the scale of x. Then we also have beta 2, which is the same thing for z now. That's the value of y, the change in y for z. But the hard part about this is we actually have an interaction of x and z, potentially. That interaction I mentioned earlier when we talked about, not on the video, but on the in the beginning of class, we talked about moderation, right? So it turns out when we interpreted x here, and I said beta 1 is the value, the change in y for a one unit increase in x. Well, if I increase x over here, right, that means it's actually not the increase in y. If x goes up 1, it goes up 1 both for beta 1 and for beta 3. So when you have an interaction, that main effect is now called a conditional main effect, meaning the only way I can interpret it in the same way as I did without the interaction is if the interacting variable, in this case z, has to be 0. Right? So if z is equal to 0, I don't have to worry about the increase of x multiplying beta 3. I have to worry about just this. So oftentimes we call that a simple main effect or a conditional main effect. I don't know if you've heard those terms, but that is it. Interestingly, interactions, I'm focusing on this class because interactions are incredibly difficult to interpret. There are plethora of journal articles published every month where you can go and look at interactions and models and see interpretations that don't follow it. And I think learning about interaction really tells you a whole lot. Like, it takes your knowledge of prediction and just steps it, or explanation steps it up further. How we doing? All right. I want to keep asking that because I'm like over here trying to make sure I'm communicating well. I don't want to just talk at you. Questions so far? So then why I'm highlighting these values. I actually borrowed this. This is something I took from Lisa Hoffman in her early days of being professor. The model for the means gives us the predicted values, right? So if you're going to say, what's the predicted value of y? Well, we sort of disregard error because actually the average error is 0. So we sort of say, if error were 0, then I can form a predicted value of y by plugging in the numbers for all the betas and that person's x and z, right? And then plugging them in, get a predicted value. Turns out, if we were to conceptualize that, well, let me stop there. I'll tell you why it's modeled for the means in just a bit. Actually, no, I'll tell you now. This is the average that we would expect a person's prediction to be. It's actually the mean, right, of that prediction. And if we were to talk about how much variation there is, then we'd have to enter in things like what's the variance of error, right? And if you remember if you took regression class, I imagine you talked about prediction intervals, like where you were to predict a person's value, but then you wanted to put a confidence or a range around it. And there was some for the average person, or there was the individual observation. That's where all that is coming from, where you see this. So the model for the variance, it's really not a model in this case. So this is saying how you look at this symbol here, if you haven't seen it before, this error or residual term for a person, this tilde character right here, you can read this as saying is distributed as. And sometimes we actually use a little bit more jargon. Each of the errors are identically and independently distributed as. So that's identically means has the same error, and independently means there's no correlation between the two, which you actually don't see there. But that's what this tilde means. So error, I will just say follows or is distributed as, it's normally distributed, and that's that assumption of normality that comes in. And the mean of error has to be 0, and then it has the variance of error here. Now, I'm not getting into what you probably got into in regression and ANOVA, which was the F table. Do you remember the F table? And there was the mean square error. That is what I'm calling sigma squared, right there. That mean square error in your table is an unbiased estimate of the residual variance. That's it. Let's see, there we go. So we're going to return to this normal distribution in a few weeks, but just know that there's 2 terms for it. That's the main thing. So let's go and predict the person's weight, shall we? We're going to build a model predicting a person's weight using height and sex as predictors, or female as predictors. Several models we will build are done for didactic purposes. So I just want to show them first, and then we wouldn't necessarily do this. This is what I'm saying, right? And I just wanted to do that because my goal, when we get into a model-based version of statistics, you quickly lose sight of the data. And that's where you're like, does it work? Should I even do it? Does it fit the data? So I'm going to start with something called an empty model, which is no predictors at all. Doesn't look, it's just an intercept. But I'm doing that because the parameters of that model map onto the mean and the variance. And then, so now you have your tie. Oh, this really is data, right? This really is not just weird model parameters. But our ending model is one where both predictors and their interaction are going to predict weight. Okay?
Quick question.
Yeah.
GLM, is it general or generalized?
It's used for both. In this case, in the context, it is general.
Why is it used for both?
Because it's just the acronym. And because someone said, oh, it's not general, it's generalized. I think more generally, GLM refers to this type of normal error linear model. And actually, I probably would just say linear model. Like if you think of the R function for regression, it's LM. That's probably what's more common, but I wanted to sort of distinguish. Sometimes people said general linear model. Good question. Okay, so here's the empty model, right? We're going to take weight. Well, we're not predicting it with anything, so we put an intercept there. We have an error there. I use the LM function R, but I'm not showing that to you. But I will note to you that the intercept I got for an estimate, you'll have to trust me, but you can run it in R yourself, 183.4, turned out that was our overall grand mean of weight. If we remember the descriptive statistics, that's the mean, exactly. Not only that, sigma squared error, 3,000, my God, 3,179.1 with no standard error. Interestingly, why is there no standard error? We'll get to that in just a bit. That was the variance of weight. So if you literally want to quickly get a variance in descriptive statistics, throw it in LM and have outcome tilde 1, you get the mean and the variance, are unbiased. Now, I will note this 12.61 is the standard error of the mean, right? And often in the statistical models that we get into, the standard error of the statistic that tells you how much variation there is in the mean, well, it turns out that is actually this value, the square root of this value divided by n. It's the standard error of the mean from basic statistics, like you learned, like you were mentioning the sort of, if you were to do this same sample over and over again, it's sort of how much all the means vary, as you mentioned earlier. There we go. And classically, again, this comes from the mean square error of an F table. But when you did a linear mixed model, did you have an F table?
No.
That's right. F tables go away. In fact, it's interesting. We spend a ton of time drilling F tables in regression and introductory statistics, only for them to leave the scene immediately shortly thereafter. So what do you do then, right? So this is where I'm trying to bring this about here to revisit what you might know already in a context of, oh, yeah, it's still there. Turns out, the reason standard error here is not given is that to calculate it in least squares, which is how this is estimated, which we'll get into later in class, is very difficult. However, in your, did you use LME or an R?
And lemur.
And, yeah, Glimmer. Yeah, GLMer or whatever.
LME.
LME4, right?
Yes.
Yep, got it. So in that package, you got it actually told you, actually it said residual standard deviation, but it gave you a standard deviation for it.
Yes, it did.
And so what's the difference, right? The difference is in maximum likelihood, which is what more advanced models are estimated in, the calculation of standard error or those terms like that is much more straightforward and easy to do in a computer, not easy to do by hand at all. And so it's always been odd to me that we talk about the concept of variation for parameters, and then when we get a mean square error, there's no standard, there's no variation given for that. And if you think of variance as being, as I mentioned before, your confidence in your result, right? And you want less, well, the standard error of the variance would tell you how confident you are your variance is accurate. So how confident that your indicator of confidence should work. And that, it's just, sorry, it gets down the rabbit hole. Maybe this is not good for 7:25 at night. All right, so now let's plug in height and predict weight from height. Here, we plug this in. We'll just interpret the parameters. Beta 1 is the slope for height. Beta 0 is still the intercept, and we still have a residual variance. That's just sigma squared error, so there's 3 parameters. The intercept is now the predicted value of weight for a person with height equals 0. That's really nonsense, right? Yeah, the weight of a height, we should get to a weight where a negative weight, that is interesting. I mean, I don't even know physically if that's possible, right? Maybe some type of quantum physics or something. I don't even know. We could center height. I'm going to do that in the next model and then change where the location of it happens to be. Location, by the way, is another term for intercept. If you hear me say that, I'm sorry. I should keep my terms consistent. Beta 1 represents the change in our predicted value of weight for a 1 unit increase in height. Now, remember, in height is measured in inches. So 1 unit would be 1 inch in this case. So every time height goes up by 1 inch, a person's weight goes up by 6 pounds, is what this is saying. That 1 inch of height really, really weighs a lot, I guess. And then, of course, you have its standard error as well. And then here, sigma squared error is now 1,218. Standard error is not given. That is our residual variance. You can see it's a lot smaller than our previous version. And if we calculate the difference of the previous version from this one relative to what the previous was, that would be what we call our R squared, our coefficient of determination. So it's literally the difference in residual variances, right? And there you have it. There's other interpretations of R squared too, but we'll go save those for now. But if we wanted to talk about centering in this case doesn't change anything except for the place of the mean. But where centering becomes really important is in interactions. Because in the interaction variable, remember the main effects depend on the other variable being 0, right? And if that variable is way away from its mean, those main effects look odd, just really far off. I don't know if you ever run a model with an interaction. If you run it without and run it and add it, and the variables aren't centered, you get all sorts of weird numbers for the main effects. But again, they're conditional main effects. But yes, this is, again, when we center it, if we centered it at the mean of height in our sample, right, then we literally get back to that mean of height for our intercept. But in many cases, intercepts are not as informative to us. So we don't often see that in linear models, general linear models with no interactions. We rarely see it, but interactions are where it really matters. Again, the other parameters, the slope is unchanged, the standard error of the slope is unchanged, and the residual variance is unchanged. So centering doesn't change anything but the intercept in a model without interactions. But if we center the interactions, that changes the main effects in the intercept. So it's an interesting layering of, this is foreshadowing needing to center for interactions a little bit better. And here is our fit plot for weight. This is an old plot. This is back when I used to use SAS. There's our regression line. It seems to not fit anybody, right? And if we were to look at these residuals, I'm pretty sure we would say these are not normally distributed. But I didn't do that. We could do it in a hypothesis test. Remember that? We could test whether the hypothesis of a slope is equal to 0 or not. We have actually two options for this. We have the sums of squares from the ANOVA table. And then there's this other option. So if you remember, there's the ANOVA table. When you do your model, there's the ANOVA table, and you can see the p-value there. But then there's also the table of parameter or the coefficients, like the regression slope. And they would have the slope, they would have the standard error, and they'd have like a t statistic. That t statistic sometimes is called a Wald test. I put that in quotes because the Wald test actually does the same thing. It just divides the slope by the standard error of the slope, and it compares it to a normal distribution, whereas this version of it adjusts for finite samples, so it uses a t distribution, and the t, if you square that, you get the f in the f table. In this case, it's not always the case for more complicated models. But yes, when I was looking at this slide here, the first thing I look at is I think, oh, if you give me a parameter and you divide it by its standard error, that's your test statistic. And I don't like to talk about test statistics because it makes me think of doing things by hand, and I don't do anything by hand. But a quick reference, 6 divided by 1 gives you a value of 6, right? Do you remember in your intro stat, do you ever talk about the similarity of t and normal? Like as like if you look at degrees of freedom of t, that's its parameter. As it gets to about 25, t looks like a normal distribution, right?
We didn't have mine.
Didn't talk about that. Okay, so I won't bore you with those details. But if you remember, a normal distribution has critical values, like a 1.96 is where like a 0.05, yeah, right, or 2, right? So if you want a quick way of checking if a parameter might be non-zero, look at the ratio of the estimate to its standard error. If it's bigger than 2, it's likely significant, or smaller than -2 also. It's two-tailed test, right? Remember those terms. Turns out that test itself, why it's enabled, is maximum likelihood. And even though we're using least squares, it's equivalent to maximum likelihood here. So the likelihood-based models have quick ways of giving you parameter tests. And so this is one of the reasons why the F tables disappear. First of all, they're not calculated. But second, this ratio of parameter to standard error parameter really is your guide to significance. And that happens when you use maximum likelihood, period. The end. If you use maximum likelihood, it's always there. Why it's happening here is because this is actually equivalent to what maximum likelihood would happen. All right. We can do the same thing with predicting weight from sex. Now, again, I wouldn't run it in this order. I just showed that height mattered. I wouldn't take height out and then run sex, because now I have two ways of predicting weight. They both can't be right. Bless you. Here, we would call this analysis of variance, because it's a categorical predictor. We have to code it into a number. So we use the number 1 to represent a female, and a 0 to represent a male or non-female in this case. And here, what we end up seeing is the intercept represents the predicted value of a weight when female equals 0. So that means the predicted value of weight for males. So another way of putting that is that's the mean weight for males. Men weigh 235.9 pounds. Another small tidbit of fact for me, I'm never at one weight in my life, and I was most recently at 235.9 pounds this last year. So yes, it was I fluctuate quite a bit, and I will tell you that not all men are 235. This is a very beefy sample of men. Sorry. And then for females, what the regression slope then means is the difference from the intercept for a 1 unit change in female. So now we know that female, the variable can either be 0 or 1. So 1 represents the 1 unit change. So that means that this parameter represents the difference in weight between men and women. So that women's average weight would be 235.9 minus 105.0, which again, I don't know that this.
Every female alive.
I am never. I am never going to ever weight shame anybody too big or too small because I don't know what the size is, and I'm not going to touch that one. I can say that about me because, yes, I have had a problem with weight my entire life. I'm currently trying to battle it the best I can. I'm doing all right now, but I've lost lots. I can't tell you the number of times I've lost 50 pounds in my life. That's how sad it is, right? And so, yes.
235 minus 105, that was.
130 pounds. Yeah, that's yeah. No, yeah, I was going to say nobody's and yeah, and BMI for me is a terrible predictor as well. Yes. So sorry, I realize this is probably not the right topic. I thought, oh, we can all relate to weight, but this is why these are simulated data. Is where I'm going for this.
Also explains the bimodal distribution.
Also true, yeah, absolutely. And again, look at that. Hey, because of this big difference and because of that bimodal distribution, turns out sex by itself describes 90.8% of variance in weight, right? So that's incredible. So this is just what I talked about with the mean. I'm just going to keep going. There is our distribution of weight. Yeah, I was going to say like the lightest male is 200 pounds, right? So this must be like a football team. I don't know. And even then, I don't think that's the case, right? Maybe wrestler. Oh no, heavyweight boxers. I don't know who that would be. Anyway, now here's the ANCOVA version, right? Which is we need to really control for the height of a person in addition to the sex of a person, right? And when we do that, now again, we interpret the intercept as the predicted value of weight when height is 0. So in this case, height is 0 because it's centered. It's a person who's at the average height, which turns out in our sample is nobody, but yeah, average height. And when a person is a male, right? F equals 0 is a male or non-female. And so that means a male at an average of an average height would be 224.256 pounds. Beta 1 still represents the change in that for every 1 unit change in height. So every 1 pound increase brings about a 2.7 pound increase in weight for that. And you can see our T statistics here. That's, again, the ratio 2.7 divided by 0.15. That's going to be very large so that we know that's significant. And now the residual variance is 16. And I didn't calculate the R squared, but you can see we're getting close to 0 here. A 0 residual variance means an R squared of 1. Right? It's also hard to do unless you simulate data. All right. So when we do that, we can actually have 2 regression lines, right? If you think of it, if we condition on males or condition on females, we get 2 different lines. And here is what we have, right? We have our weight for each. What we just basically do is when for female would be 1. So this coefficient, we multiply it by 1. That negative 81 is applied to the intercept, and we get 144 as the intercept for females. And we get 224 when F is 0. That just knocks this part out. We get 224, which is original intercept. But you'll note the slope is the same. So what this ANCOVA assumes is that equal slopes. And I assume you probably in regression class you talked about ANCOVA, and this was an assumption of ANCOVA. It's an odd thing. When I learned since I've been doing this a long time, we've always had interactions, and we can just throw an interaction in the variable, but that somehow in lots of textbooks isn't called analysis covariance.
Yeah, we use the term. We didn't, but we didn't call it ANCOVA.
I'm glad. That's good. I have to put these in here because it's like some people get trained, that's ANCOVA, and it's a violation of the ANCOVA assumption to have a different slope. But this is why I'm introducing interactions to you, because when you put an interaction in right here, this right here, the interaction of height and sex, you end up getting a more appropriate model. It doesn't actually call, it's not actually labeled ENCOVA. Like you said, is it ENCOVA? I didn't use that term. Really glad to hear that.
It was more so like we really just called it was regression with categorical
Perfect.
predictor.
Perfect.
I think
That's exactly it. No, and it's
like, now I'm there.
when I was in
That's what it was.
when I was an undergraduate, or I was an undergraduate, they would never introduce this. It was almost like they were like risk averse of saying anything about interactions at all. It was almost like, and so this is ANCOVA. Well, ANCOVA 1960s, we didn't have interactions as much, I guess. Probably was there too. But now, again, this interaction, beta 0 represents now the predicted value where all the variables are. So again, this is the predicted value of a man who's at the average height, 222.184. That's significant. Now, beta 1, though, is the simple main effect of height, right? We would call that the simple main effect because, have you heard that term, simple main effect? Anybody?
Just my dissertation. I don't know if it's not Chomsky used.
Okay. Conditional main effect, maybe? Anybody? Neither. Cool. I got a chance to teach now. Perfect. I'm only asking not to criticize, but more like if I'm being redundant with your training, I don't want to do that. But if I can add on, I'm here. All right. Again, simple or conditional main effect, because beta 1 or height is in two places. You can't just say for every 1 unit of height increase, beta 1 is the increase in weight, right? You have to say for every 1 unit of height, beta 1 is the increase in weight when F is 0. So for men, this is the slope for men, is what that indicates, right? We go further, right? Beta 2 is the simple main effect of sex, right? It's the change, and again, it's simple or conditional because it shows up, or height shows up in that interaction, right? So now we're saying that is the change or the difference between men and women's average height for a man and a woman at the average height, right? So a male who's at 183 and a female who's at 183, the female should be 82 pounds less than the male when they're both 183 some odd inches for height. Kind of weird, right? Then finally, the interaction itself. This is where we'd say, oh, wait, interactions are interesting, right? You have two variables there. You can condition on one, you can condition on another. My goodness, this clock is slow. I got to hurry. We're almost done. Sorry. This is now saying height or weight. Weight is height is moderated by sex, or sex is moderated by height. That is what it's saying if this is significant, which it is. And so what this talks about, this is the change, the additional change in the predicted value of weight for a change in either height or sex. And it's so this basically what we're going to find, and I can't do that. I don't have time for this now, but in a couple of weeks we'll get back to this. What we're going to find is this is actually what moderates or changes the main effects. If you were to go and talk about what is the line, or what is the main effect when we want to go at that interaction goes there. So, all right. This is right here, by the way, the normal distribution where the normal needs to be applied. I'll say that last thing right here. These are residual values. This was our distribution of weight, but this is the distribution of residuals for weight. It's not entirely normal, but you'll see it's a lot more so. This is the normal distribution superimposed on top. All right. I'm sorry to run us out of time. I've got less than 1 minute left. Thank you, everybody, for being here. I want you to know that I'm trying to give you your money's worth for taking this class, or your time's worth, even if it's hard to get to 7:45 p.m. or 6:45 for you, Colin. So thanks, everybody. If you have questions, I'm happy to stick around afterwards. But those of you who don't, you're welcome to go. I will be wrapping up. So thank you. And I hope to see you next week. We'll talk about our next week, okay? Nothing. I will send out a note on Canvas to talk about it. Please have RStudio, but actually next week I'm also going to show you how to download Visual Studio Code or Positron or whatever, and just try each of those out. Sound good? All right. Thank you all. It's been a pleasure teaching you today. Thank you. Hope to see you again. I hope you want to come back, but okay. That's what I'm going to keep saying that. I'm going to keep saying that. Yeah, absolutely. Hang on one second. Let me